were discussing about the characteristic impedance, right? And the representation of input impedance. And yeah, we were looking at the four cases, I guess, correct? So as we can see here, the various cases. First, we wrote the equation for input impedance, Zin in terms of Z0 and ZL, right? Then we modified according to the various types, short circuited, open circuited, right? Lossless, and even the quarter wave transformer, right? So, okay, let's move further. The next topic is called as the concept of standing waves. Right. Now, let's directly start with the equation which we know now. So, if I want to measure the voltage on a line at some point located Z from the sending end, right? So, that we can write it as any voltage equation V, which we have commonly written. So, that is V is equal to, right, the source voltage Vs e to the power minus j beta z plus Vr e to the j beta z. So again, I'm not writing a gamma here. I'm writing beta. So I have to mention what I am trying to write. So this is the voltage at any point, that is z. Any point z uh, from the sending end, correct? Sending end on. So when you see, you don't write a alpha value, in the sense the gamma is replaced as j beta or minus j beta, means it is lossless line. Okay, so we are talking about a lossless line. Okay, so that means standing waves, actually this concept is related to the lossless lines. Okay, so sending end on a, yes, lossless transmission. Okay, now, so what we try to do here is we will try to put we will make a small modification, because normally the standing waves, or the one term that is related to the standing wave, it is called as a SWR, standing wave ratio. We are going to define soon after we look at this concept. Okay, so that is actually measured somewhat with respect to the load end, not from the source end. Okay, so because of that, now I need to bring another term over here which tries to represent the length of the line, as well as where you are measuring from the load. Okay, at what point, right? So as of now, I'm simply talking about the point which is measured at a location Z from the source. Okay, right. Let's try to slightly modify this with the help of a diagram, wherein you can see that I'll try to consider the distance from the load as my parameter. Okay, right. So we'll try to write one. Okay, let's try to write a diagram. All right, now, so this is the side where we are considering the load. Okay, so this is, say, ZL, indicating that there is a load, right? So we already have a representation for the total length of the line. Let's keep that same. All right, let's not change it. So if you remember, we used to represent the length of the line as the small letter L is the total. Now, just now I mentioned, I say I have a point Z that is measuring from the sending end. Maybe I'll try to mark this is the point which I'm talking about. Correct? So, as per our discussion so far, right, this is the distance which I'm measuring. That's is Z. Let me write. This is a Z. So, now the remaining length will be the distance. Correct? So, that's the distance of the point from the load. Correct. Let me denote that as X, right? So now what I try to do is that I'll try to write this. I can try to replace this Z in terms of L and X. Correct. Because equation cannot be changed. Once I say correct, once I say that I'm measuring, I have to represent this itself in my equation. It has to be Z, but you can definitely bring other variables in this location. That's all. Correct. So right, as we know now, Z plus X is equal to L, right? If you want to write that as Z, this should be L minus X. Correct. So I can write but so let's say Z plus X is equal to L, which implies if I want to write about the Z, that should be equal to L minus X, right? This is my one equation. Say this is equation number two. I also want to bring something more into place. That is, I have the V. Okay, let me show the equation once. Yeah, so I have the equation V is equal to Vs e power minus j beta z plus Vr into e power plus j beta z. So let me take the Vs common from this. All right, so when the Vs moves out, correct, what happens? Vr by Vs, I can bring a sigma over there, isn't it? Okay, so let's try to put that as well in this equation. So first, let me write what happens to the V now. So V is equal to Vs into e to the power minus j beta into z is equal to L minus X, isn't it? Okay, so this is L minus X plus Vr e to the power plus j beta into L minus X. Correct? I can see that the j beta L may be a common term. Can I take j beta L? I'll take a minus j beta L out. Okay, so for some reason, let me try to take. So this means it is Vs. I'll take a Vs out later. So let me try to take that e to the power, this term first, e to the power minus j beta L. I'll try to take this out. Okay, so what remains inside is first term, that is Vs e to the power minus of that minus, I think that becomes a plus, right? So minus j beta into minus j beta L, I'm trying to take it out. I'll multiply first, in the sense first I'll multiply e to the power minus j beta L into e to the power plus j beta X. That's what is remaining, correct? So okay, so plus j beta X. Then on the others, in the other term, this is Vr into e to the power, right? I have it correct. So e to the power minus j beta X. Fine. Okay, now let's do the other thing which I mentioned, right? I'll try to take out a Vs as well out. So this is Vs into e to the power minus j beta L into it's the same term, e to the power j beta X. Now instead of Vr by Vs, can I write the rho here? Correct? Right? So rho times e to the power minus j beta X. So now you see, we got the equation in a format wherein I have the distance that is measured from the load end, plus the total length of the line present, right? So this is okay for us, right? So this is the equation we are going to hold for the time being, right? Let me call this is equation number 3. Now let us consider the, so here onwards we have actually two different things to study. One will be for a short circuit, right? One will be for the open circuit, right? Because depending on that, the standing wave pattern changes. Okay, so because of that, we have to deviate from here. So let's take a case of number 1. So this is the main equation, whatever we have obtained so far. That's the equation for B. But now we'll make a slight modification, right? So what can you tell me, what is the rho value for a short circuited line? Yes, for a short circuited line, this is what we know, right? Rho is equal to, can you check? Rho is, so case 1, you can see, right? Rho is equal to -1. Can you see here? Short circuited load. Yes, you remember? Okay. So that means rho should be equal to -1. So that means just check what's going to happen here, right? This implies update your equation number 3. That is V is equal to Vs e to the power minus j beta L e to the power j beta x plus minus, right? Because it's a -1. So rho is -1. So minus of e to the power minus j beta x. Right. Now, I know from trigonometry, if you have e to the j theta minus e to the power minus j theta divided by, if you have division by 2j, then this can be written as sine theta. Right. So now I see that I don't see a 2j in the denominator. So I need to multiply and divide by 2j. So just do that. So multiply by j2 divided by j2. So whatever in the denominator, you are going to use it, right, for the writing the sine function. So this implies the v is equal to, there is a j2 because of the multiplication in the numerator into vs, right? E to the, I'll write even the e to the power as it is, e to the power minus j beta L into, it's a sine theta, so it's sine beta x, right? So that is the equation we will be writing for the magnitude. Right. Now, if you want to, this is again, this, I can see that this is the equation for voltage, right? If you want to measure the voltage, I can take the magnitude, right? So that means, so this implies taking, taking the magnitude. So that is magnitude of V is equal to magnitude of J to Vs e to the power minus J beta L into sine of beta x. Okay, so what should be the magnitude of this thing? Can you tell me what I can write here? So J will not come. J is not a magnitude. Huh. Yeah, okay. So we'll write only those two terms here. 2 Vs into sine beta x, right? Again, see, since you are taking the magnitude, now you see there is a change. This is 2 Vs into magnitude of sine beta x. Are you okay with that? Because sine beta x takes positive and negative, right, throughout. But I have to make it, since I'm taking the magnitude of this whole function, whatever you get for a sine wave, I should take the magnitude of that. In the sense, it's not going to be negative. All right. So this is the equation for the voltage which appears on the line. Okay, so this you see, this is a standing wave. Okay, so I'll try to draw that. No. All right, I'll show you the equation. Now you see, it's actually x is measured from where? X is measured from the load end, right? From the load, if I, in the sense, my negative z direction is x. Okay, basically. All right, so let's try to draw a wave, right? So let me call that, this is the 2vs point form, right? So this I'll hold this to be 0. This is 0. Okay, so again, this the horizontal axis is the my length of the line, complete length. All right. So as you know now, sine 0 is 0. So my wave should start from 0 itself, right? Wave will start from this point. That's the first thing, right? And I know that as I move away from this in this direction, x increases. So sine 0 is 0. As sine will increase, yeah. So it actually increases. I'll just draw this thing. Yeah, yeah. Please tell. Please go ahead. Hmm. Right. Rectified. Correct. Every negative cycle will be the positive cycle. That's all. Correct. Because it's a rectified. So I normally I have, let me say this is a 0. I'll just try to mark some points like this maybe. Okay. So what exactly is happening is, right, I will get one wave over here. This is my one half cycle. Correct. But I am expecting a negative half cycle here. That's not going to happen. Correct. Because right. So you will get a positive once again. That's all. Right. So like this, you keep getting, right, the wave. So this is the uh, pattern we are going to get for a standing wave in case of a short circuited line. Is it clear? All right. So next, let's go to the case number 2. So the case 2 will be, right, the open circuited line. Right. What's the condition for open circuited line? So the value of rho should be equal to 1, correct? Right. So open circuited line, this means the rho is equal to 1. Now update that equation once again. So 3 becomes equal to, we have V is equal to Vs e to the power beta L into, this is e to the power minus, sorry, my mistake. First one is positive, second one is negative, right? So e to the power j beta x plus e to the power minus j beta x. So we have the representation e to the j theta plus e to the minus j theta by 2. Okay, can be written as a cos theta. So that means I need to multiply and divide it by 2 to this. So simply you multiply by 2 and divide by 2. Right. So the one which is in the numerator can be directly taken. Right. So this implies V is equal to 2 times the Vs e power, correct, j beta L into, right, so this is cos beta x. So that means, right, magnitude of V is equal to, it's 2 Vs magnitude of cos beta x. So the difference is that we can see, right, whenever the uh, yeah, it's a cos function. So whenever I put x equal to 0, it is highest, correct? So highest means it's going to start from 2 Vs now. That's the basic difference. Yes. So we'll mark the 2 Vs here. So actually there is a small shift compared to your previous waveform. Okay, it begins from highest value and comes down to 0, right? Then it actually repeats. This is also going to be the rectified waveform, right? And so on. Right. So this is a 0, right? And as we move to this line, we are trying to measure the x. Okay. All right. So that's the difference. Now we'll go for the other format. Other than these two, the standard format is you have some other values of ZL. Right. So this is case number 3, right? The ZL will be written as RL plus J times XL. So in this case, right, this is a complex load. This means, what's the meaning of this? What will be the value of rho? Rho is also complex, correct? Do you remember? Right. So now the rho is complex. Now the minima value will not be 0 and maxima value, right, will not be 2 Vs. It's actually lesser than that because, right, because of the fact that one ZL is complex and the rho is also complex, right? So always we have, right, what you call maxima and minima present, right? I'll tell you how to calculate the maximum value and the minimum value as well, right, slightly later. Okay, so in this case I need to write one sentence here before I draw, right? So ZL is complex, rho is also complex, so because of that, uh, okay, we can write one sentence like this: the minima uh, is, okay, minimum values are not equal to 0 and the maxima will not be equal to 2 Vs or magnitude of 2 Vs, whatever. Okay, it's not going to reach that. Now previously we could see that, right? It is reaching 2 Vs and, right, 0. That's not going to happen. But I'll ask you one question from any of the previous graph. What should be the gap between this and this? What should be this distance? Distance between maxima or distance between minima? If I want to measure, what's your answer? Even this distance, it's going to remain same. So what is this? Can you measure it in terms of maybe lambda? It's lambda? Uh, no, in this graph, it may not be visible, but consider the lambda, right? Because in the original waveform, right, I may have a crest here. This will be a trough. So this will be a crest, this will be a trough, and so on. Now you tell me which is lambda. Considering the black colored graph. See, original graph is what I have drawn just now, correct? The black color. So, so there, so that should be lambda, right? So lambda is from here to here, isn't it? So what's if that is the lambda, right? What is this now? What I have marked here? It's half of the lambda, right? So yes, so that's right. So this has to be the lambda by 2. So in the sense, maximas are separated by lambda by 2, even the minimas are separated by the lambda by 2. This is true even for the previous graph, okay? I have not drawn here. It's going to remain same, right? So that's the point here. So there will be no minima touching zeros, no maxima touching VS, 2 Vs. but still the adjacent minimas and maximas are still separated by lambda by 2, irrespective of the value of rho, right? I can write that point here. So adjacent minima are separated by lambda by 2. So uh, again, this was a concept of right, what you call as the standing waves. Again, we considered only voltages here, but definitely the similar concept can even be explained by taking current as reference, because right, the equations still remain same, right? I is equal to is e power minus j beta z my plus vr e to the power j beta z, right? So that's the equation. For that we can still write the same case, isn't it? So even for currents, you can do that if it is required. That's the point. Is it okay? Yes. Now you see we have two values. One is magnitude of V max, right? And magnitude min. Okay. So now it is not required that you have to start from a specific point. Any point you can start. All right. So maybe I'll start from here. Okay, so this is how the standing wave looks like in case of, yes, load being complex. All right, let's proceed further. Now I'll try to define what is called as, okay, what is the condition for having the minima and the maxima? Do you remember? It is, directly, I'll write one point here because I need them to find the standing wave ratio. All right. So before that, let's just try to recall something from physics or anywhere you studied the waves topics. Okay, the crest, the trough, where the crest occurs, where the trough occurs, what's the condition, etc. Somewhere we might have studied. So the point is that if you want to find out a minima, right? What is a condition? uh, how do you find out that whether there is a minima or maxima? Yes, 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 yes. What is the condition for minima or maxima? Okay, maybe I'll make it more clear. I'll move ahead and I'll bring the concept slightly later so that it's relevant now. So even I can talk something about the specific cases here so that I can find out what is okay. Okay, I'll give an example. Since I started, I'll talk about this now. So consider, say, the first one we draw. That's a case one. Okay. Now you tell me what is the condition for minima here. So I just want to relate this to a minima. Right now you see this V becomes minima or zero whenever sine beta x is equal to zero. Correct? Okay. Now you tell me what is the condition? What is the condition that you can put? Yes, beta x equal to something. What is that? It can be any pi, right? N pi. So beta x, right? So now you see I'll just write in bracket. So this is beta x is equal to n pi, correct? Now, what I can do, I can substitute for beta, correct? So beta is what? Beta is 2 pi by lambda, correct? Now that means whenever I can also try to rewrite this as, so that means I try to find all positions of x where the wave is going to reach the minimum value. Okay, x is equal to what? N pi by beta, correct? So substitute, that is n pi divided by beta is 2 pi by lambda. So pi, pi cancels. N times lambda by 2. See, that's what is the point, right? So that due to this, we wrote every lambda by 2, there is maxima or minima. The same thing will hold good even for the maxima. Okay. So anyway, so you see that put n is equal to, when you put n equal to 1, that is this distance. From the load, I moved the distance of lambda by 2. So I got my first minima, right? So move one more lambda by 2, put n equal to 2. So at a distance of lambda, you have another minima. That's over here. That's the concept. Okay, right. Anyway, so one we did. Now anyway, we can apply this if we require for other cases as well. Okay, we'll do that later, right? I'll come back to this. Now anyway, I'll move ahead to the definition of what is called as the voltage standing wave ratio. Okay, so this is a very important parameter. This is, in short, you will call this as VSWR. Okay, this is voltage standing wave ratio. Now, this is a ratio, means I have to take a ratio of something. What do? You take the ratio of, right, the maximum voltage that is present on your line, that is Vmax, and the Vmin, right? Vmax, Vmin, both we have marked, right? So like this is the Vmax, this is the Vmin, right? So you take a ratios of Vmax to Vmin and you call it as the standing wave ratio denoted by capital S. Okay, right. Now, how much standing wave exists, right? What is the percentage? Magnitude of the standing waves can be measured using this VSWR. So I'll write 1 point. So this is used to measure the magnitude of the standing waves, right? So that's what we are going to use. Now how do you measure it? So uh, the voltage maximas and voltage minimas, right, we'll try to take a ratio, right? It is the ratio of, it is a ratio of voltage maxima, voltage maxima V max to the voltage minimum on a transmission line. Okay, right. So how do you denote that? It is S is equal to magnitude V max divided by magnitude V minimum. Okay, now uh, if at all I want to represent the V max along my line, okay, so what we should do, let's try to take that. So first let's once again start from our equation V. So V is equal to, uh, I think we started with Vs and we converted, there is a what you call, uh, there is the beta L format. Just recall this, it's in the previous section. We got minus j beta L in place, L and X, correct? e to the power j beta x plus rho times, right, e to the power minus j beta x. Are you fine with this equation? I'll show you. Yeah. So you see here, this the equation number 3 is what I have copied. Okay, this equation 3, just now we started the discussion about the standing waves, right? So there you can see initially we started with the regular equation of voltage at any point on the line in terms of Z. Then in order to bring the distance from the load, right, we modified and we wrote it like this, equation number 3. Is it okay? Right. So just see, I'm writing that. So this is what I will start with. We know that. Already we know. So I'll just write it. Okay. All right. So from here, now you see I want a V max, correct? So in order to get a max, right? Let me, I want to find, this means if you want to find V max and a magnitude, so it's very clear now. I'm not writing the phase terms, correct? So in other words, okay, I'll make a small modification here itself, because this can also be written as V as e to the power minus j beta L into e to the power j beta x. You see, this is what we have not written so far. I'll write it as magnitude rho e to the power j psi. Are you okay? Because magnitude r, the rho is a complex number, right? So I can write it that way. So now it becomes more clear when I write a next step. Okay, so into e to the power minus j beta x. Anyway, we can club and we can write, no issues, right? So these two can be clubbed. Absolutely fine. Okay, so now I want a magnitude and it should be maximum. Correct? So the maximum point is possible whenever I have, let me try to write this. There is a Vs, which is definitely no problem. It's a magnitude term and it is positive. Okay. Now, the term, what is the magnitude here? Magnitude of e to the power j beta x, it's 1. So open a bracket, write 1 there because that's the magnitude. 1 plus, yes, the magnitude of rho. Correct? So this is the maximum value which it can attain. Right? So that's a Vmax. Right. Now, uh, let's try to write the condition required for the minimum, right? So that also I'm writing the V min is equal to, it has to be Vs only, right? Into the first term, anyway, there is no positive negative, but the second term, there is a possibility that this is becoming negative, correct? We already have seen that sine or cos, depending upon that, there is a possibility of the term becoming negative, correct? So that means this is minus magnitude rho, right, is the minimum value, correct? Vmax and Vmin. So substitute these two to get the equation for S. So I'll call this is, maybe this is 1, correct? So this is perfect. So this implies I can get 2 in 1 to get S is equal to 1 plus magnitude of rho divided by 1 minus magnitude of rho. Okay, right. Now, once again, we will definitely discuss about, okay, so let's do a conversion, right? I want, can you convert this into a format wherein I am able to get the equation of rho in terms of S. There should be S in this side. Can you cross multiply and get this? Yeah, yeah, yeah. Please do that. Sure, take your time. So when you simplify, you're going to get this. Perfect. So this is s minus 1 by s plus 1. Okay, let's try to explore further. So because of this one, now I have to, I know that the row value is minus 1 to plus 1, correct? Right? Since a row is equal to, so I will do this one small exercise now. That's going to be helpful in problems, right? So for that reason, okay. So that is since minus 1 less than or equal to the row value less than or equal to plus 1. Now let's take the cases. So case number 1, right? As usual, it's a short circuit. Okay, short circuit load or short circuited line. Rho is equal to minus 1. This implies, tell me what is S? What is the standing wave ratio? Substitute in 3, okay, equation number 3. Because rho value is known to you. Substitute rho equal to minus 1. Take a magnitude of rho, it becomes plus 1. So denominator is 1 minus 1. Infinity. So S is equal to infinity for a short circuited load. Okay, moving ahead. So this is the case number 2, right? Open circuit, right? What is a rho? Plus 1. Okay, tell me what is S? Else is infinity once again, right? So which means on a short circuited as well as open circuited load, you will find the standing wave ratio to be infinity, right? Next case, case 3. Complex in the sense I don't know the value of rho. I may not be able to, right? I may not be able to go ahead, right, with the calculation part, right? So whatever rho value you get, magnitude you will substitute. Okay, so for now, my case 3 here is a matched load. Matched load in the sense the ZL and Z0 are equal, right? Which means, right, the rho value is 0 over there, correct? Okay, now you tell me what happens to S. It's 1. Perfect. So ideal values of rho and S for designing of a transmission line is that rho should be 0, S should be 1. Is it okay? Right. I'll move to the next part here. So in this case, this is case 4. So if it is possible to recall all these cases, right, it's very good. It's wonderful. You will be able to solve the problems very quickly, irrespective of what type of question it is, right? But yes, there are so many cases, so many things to remember. Like every VSW has four cases. The previous section Z0 has 4 cases. Zin has 4 cases. Like it's difficult to remember. I know, right? In that case, you should be able to remember the main equation at least, like equation 3. Yeah, then you can substitute and you can, right, do that. All right. Okay, so for the, okay, the for case 4 is lossless line. For a lossless line, that means, you see, I don't have a ZL, I have RL. Okay, and I don't have Z naught, that is equal to a resistance, simply R naught. Correct. Now you tell me what will be the value of S. Right? I need to use this equation. The rho is modified now as RL minus R naught divided by RL plus R naught. So because of that, what happens to S, you need to tell me. Therefore, this implies S equal to, I will substitute that. So this is 1 plus uh, divided by RL plus R naught whole divided by, correct. This is 1 minus RL by Rn plus R naught. Okay, take your time, try to simplify. Denominators anyway will get cancelled after the first step, right? Get me an answer. RL by R naught. Okay, right. In the numerator, you get R naught cancelled, I guess, right? Let me just cross verify. RL. Huh. Huh. Okay. Minus RL plus R naught. Yes, yes, yes. RL by R. Okay. Right. So that's how we try to represent this. Let's move quickly further to write what will be the impedance at the voltage minimum or voltage maximum. Correct. So this will be our next topic. Not voltage, sorry. That's the impedance. I want to try, I want to measure the impedance at any point, right? Where the voltage is either minimum or maximum, V max or V min. What should be the impedance, right? So we'll calculate that. Impedance at V max, V max for voltage maximum, V max. So I'll just write here, or a V min. Okay. Now, so this is the equation, right? Normally, how do you measure the Z minimum? For Z minimum, it should be uh, voltage by current, but current should be maximum. Okay. So that's our concept, right? So I can write. Okay, let me try to write here. So Z minimum will be written as, it's actually the equation generally we will be using is V minimum divided by the what you call I maximum, correct? So that's what we call as a V minimum, right? Now this is nothing but, so I can write it as Z naught into, so the minimum value will happen whenever I see voltage is 1 minus magnitude of rho, correct? Divided by maximum happens whenever it is 1 plus rho, correct? So what is this term? Whatever is inside bracket, it is 1 by S. So this is Z naught divided by S, right? So you know Z naught value, divide by the standing wave ratio, you get the minimum value. Similarly, the Z max actually is, right? It is nothing but wherever the V max occurs. V max divided by I min, right? So in order, Z naught should be there because I'm measuring in terms of Z naught only. When it reaches maximum, it is 1 plus magnitude of rho. When it is minimum, 1 minus magnitude of rho. So now the inside bracket you see S itself, correct? So that is Z naught into S. I'll write a capital S. So this is the equation for voltage maximum. Not voltage, sorry, the Z maximum, right? The impedance, maximum impedance that is obtained at every position wherever you have V maximum. Okay. Similarly, the Z min is visible to us wherever we see a V minimum on the line.